Alright, it's 11. And for the people who haven't arrived yet, do you have phone number of them? No? Okay, let's do it. Start with check who's here. Ami, not here yet. Daniel? Yes. Nan? George?
Yes.
Jer? And Yahweh?
Yes.
Okay. Alright, I hope you get your score. I will return your material later. Okay. How are you doing? Are you ready? Okay, let's continue from the previous lecture. Previously we talked about LU decomposition. Okay. We already talked about Gaussian elimination. Do you understand Gaussian elimination? Yes? Okay. Have you ever tried Gaussian elimination before? Yahweh? You should. What language? C++? What about your MATLAB too? Did you try Gaussian elimination? Did you try Gaussian elimination for two equations, two unknown? Analytically, you did. Okay. So if you have two equations, two unknown, can you solve it? Linear equation, like constant multiplied by x plus constant multiplied by y equal to another constant, and we have another equation like this. So basically you have two lines, they cross each other, and you try to find the solution of x, y that satisfy both equations simultaneously. You did that before, right? Okay. LU decomposition, like what we talked about earlier, is similar to Gaussian elimination. The benefit of it, who remember the benefit of it? Nan, do you still remember the benefit of using LU decomposition? LU decomposition has some more benefit compared to Gaussian elimination, even though they are both very similar. George, what's the benefit of using LU decomposition? It saved the memory? Okay, no need to redo. Can you read that line? No need to redo the factorization for factorization for each b. Do you understand that? What is b? B is on the right hand side, right? So previously, when we do Gaussian elimination, we combine left and right together. Okay. After we combine them together, then we do the elimination process, right? If you remember, we combine left and right, and whatever we do for the whole line, right? Whole line means not just coefficient matrix, but also the constant on the right hand side. Okay. So this means if you change the right hand side, then you have to redo the elimination process. Make sense? Okay. So every time, you see this time we have 8 minus 11 and minus 3. We append the right hand side to the coefficient matrix. So we do Gaussian elimination. When we do elimination, the operation that we do on the left side is the same that we do on the right side. So if the right side change, we have to redo the whole elimination for the right side. Good? So whatever we do with the left, we have to do on the right. So you see this thing, we have L2 plus 3 over 2 L1 become new L2. See that? So this operation has to be done on the whole line. On the left side, which is minus 3, minus 1, 2, and also on the right side, which is minus 11. So minus 11, even though it is on the right hand side, it is still has to go through this process. So this means every time that the right hand side change, we have to redo part of the Gaussian elimination. But for LU decomposition, we don't need to do something like that. So we separate or find the factor of A to be L multiplied by U. So when right hand side change, B change, we don't have to redo LU decomposition, right? A equal to L multiplied by U. It is the same regardless of B. Make sense, Daniel? Yeah, okay. So LU decomposition is very powerful. We don't have to redo it when B change, but for Gaussian elimination, we have to redo it when B change. This is the main difference, okay, that you should know. So if we have one equation, AX equal to B to solve, using Gaussian elimination and LU decomposition may have like similar speed, not that much different. But if we have 100 equations, for all equations, A is the same, but B just changed. Then this time it makes a difference. If you use LU decomposition, you have a decomposition of A just one time, and you keep reusing that, right? But for Gaussian elimination, you have to redo the whole thing every time. Make sense? Okay. After we get LU, which we will talk soon, okay, how we get that, then we do L multiplied by UX equal to B. So UX is an unknown, we call it, let's say, Y. So Ly equal to B. Then we use forward substitution to get Y, right? After we know Y will be a column vector. Then we have Ux equal to Y. U is top right triangle, right? So we can use backward substitution to get the value of X. You get it? Okay, this is the review. Alright, now how do we get L and U? How do we do LU decomposition? So there are a couple methods. I just tell you one. Okay. So first, let's set diagonal term of L to be just 1. Okay. So we have L is 1 0 0, L2 1 1 0, L3 1, L3 2, and 1. Okay. For U, the bottom left is 0, and the diagonal term is the new value. Okay. So L multiplied by U. L is 3 by 3, right? U is also 3 by 3. If we do the top left, so what we do is we have row multiplied by column. Good. So first row multiplied by first column, we have 1 multiplied by U1 1 and 0 multiplied by 0 and plus 0 multiplied by 0. So we get that. Okay. What about row 1, column 2? So row 1 is that, column 2 is that. So we have 1 multiplied by U1 2 and 0 multiplied by something and 0 multiplied by 0, which is this. Okay. For L1 3, we get that. Okay. For second row, we have this multiplied by that, right? Second row, first column. So for second row, we have L2 1 multiplied by U1 1 plus 1 multiplied by 0 plus 0 multiplied by 0. So which is this. Good. For second term, we have this multiplied by this. So basically, after you do everything, we get that matrix. Alright, so that is L multiplied by U, which is A, right? So that is A, and that is also A. Got it? So I can write it like this, right? So this means U11, if we have 1 on the diagonal term of lower triangular matrix, then we have U11 equal to A11. No question, no problem, right? U12 equal to A12. U13 equal to A13. Then we just make this equal to that, term by terms, element by element. Not much of a problem, okay? So we can write equation, then we can solve it. How do we solve it? Alright, so this thing, I don't have to worry about it, right? It's straightforward. We get the solution directly. Next step, U22 equal to A22 minus U12 L21. So U12 is from here. U12 is already known. Okay. L21 is this. Look at L21. By solving that equation, L21 is A21 divided by U11. So U11 is known, right? We solve it. U11 is known. So this means we do this, then we do this, then we can do this one. Everything on the right hand side is known. Then we can do this one, and then we can do this one. A31 divided by U11. So this means if we do it step by step, everything on the right hand side will be known and we can solve it for the left hand side. Okay. They are the compact form. Okay. After you can go through this. After we do all this step by step, we can put everything together and we get this compact form. So the compact form, to derive it, is just multiply L with U matrix. After we multiply it, we get this and we assign it to be equal to the original one, and we derive each one by one, and we see the pattern. Once we know the pattern, we can put it in a compact form. So Uij equal to Aij minus summation of k equal to 1 to I minus 1. So this equation is the same as that, you see? So when I just copy it from here, so you will see that it's the same. It's just in the compact form with the summation sign. See, L32. So basically there's a bunch of equations that we put in, and then we can get L, and we can get U. Our task is to use the right library, and if we do it manually, we have to put the equation in correctly. Question? No question. Very easy, right? Very easy, just have the formula. Okay. How do we put that formula into Python code? So eventually when we use it, we will use SciPy. No doubt about that, because it's faster. Okay. But I also want to show you, if we have the equation and we want to put it in, what do we do? And the reason that you want to know that is because sometimes you try to put some algorithm or some equation into code format. Hopefully you can do it, okay? Okay, now let's take a look. You see this one? That's equation for U. And we have equation for L. So what I do is, I do left to right, top to bottom and left to right. top to bottom mean I calculate. I try to get L and U, right? I do top to bottom, okay, row by row, and left to right. That's what I do. Okay, to do that, that's our strategy. So I have I in range of 1 to n minus 1. Okay. Then I have j in range of I. Okay. Then I do the summation. Look at this summation. A 0 colon j comma j dot dot. Do you still remember dot dot? Dot dot is the matrix multiplication. Okay. Dot, which is like period, and then dot, period, and then dot is a matrix multiplication. So if I do matrix multiplication, then I get the summation. So matrix multiplication 0 to j, and j equal to starting from 1 first, right? So the first time j equal to 1, then this is just one number, dot with maybe another one number. So I try to do this kind of thing in a quick way. Okay. Today I don't have Python. Next time, which is this Wednesday, we will use Computer Lab 212 in the middle. Okay. In the Computer Lab, I already installed Python and all library that you need. Okay. And we will try to go over step by step together. That way may be better. Is that better? So this time you will have computer to do it. Yeah, early on we have number of students more than number of seats, but now number of seats is more than number of students, and we can do it. So early on we cannot do, but it is very good that we have many people drop, so we can do it now. Good. So this code, we will play with it. Okay. So we will see what's that about. But basically we have loop for L and loop for U. So this thing is a loop for that. Why do I know that? Because I have this term minus summation divided by ijj, which is that. Okay. And loop for j, I just have aij, which is that aij, minus the summation, which is that part. Right? So this is just put the equation into the coding format. So there are several ways to write it. You don't need to do period, dot. You don't need to do this. But you can do this too. So dot, dot. So this means we have, look at this, 0 to j, comma j. That is the same as this one, right? But if you notice, I didn't use L and I didn't use U. Every time I just have A and A and A everywhere. What's that? Is that going to work? It's kind of trying to make it compact, right? So you see at the end, what do? I update A. What does it mean? So this means I go from here, which is this, to the new matrix, which is have store U value in the top right and L value on the bottom left, and I don't store the diagonal term. So like replacement. Okay. So I start. Did I write down? No, I didn't write down. So what we will have is we start with this matrix, and I replace A with L and U. L and U, they fit to each other, right? You see this and that. Do they fit to each other? Not really, because there's a diagonal term. But diagonal term, we don't have to waste the memory space to memorize all those, right? Because it's just one. So we know that it's just one. So we just say, hey, new matrix. Bottom left is L, top right is U. And then we don't create a new memory space. We just replace it with A. Can we? Yes, we can. So that's why you see, at the end of doing these two, what we just do is, we just update A. Okay? From A equal to coefficient matrix to be A that star L and U, and have U on the top right and L on the bottom right, bottom left. Why can we do that? By the way, this is the efficient way of doing it, but to really do it efficiently, you should not do it in Python, you should do it in Fortran or C++. Okay, because Python is not going to be as fast as those. Alright? Why can't we just replace it? The reason is, we never reuse. If you look at the formula, we never reuse. We use U11 equal to A11, and then we don't have to use A11 anymore. We can replace that. Okay? We use A12 just once, and then we are done. Okay? We never use it twice. Because we never use it twice, we can replace it with a new value. So we use A22 one time, and we replace with U22. Okay? We never use it twice. That's why write it like this is okay. So when we look at the summation A0j, j. So in NumPy notation, the second one is column or row. Daniel?
So, sorry, what's the question?
I have two index, first index and the second index. A is a NumPy array. For NumPy array, the second index is for row or column. Yeah, the first one is for row, right? So this means column J dot with column I. So column J may have n. So the first one will have the dimension of many row. Right? Is it many row? Yeah, many row and one column. And this one have one column and then one row and many columns. Can we dot like that? You see my point? We have something like this. The first one has, let's say, many row, right? Three row, one column. But the second matrix is just one column, one row, but many columns. So that is second matrix. And the first one is like that. You see my point? So n by 1 dot with 1 by n. We should get n by n matrix, right? If we dot like that. But for this case, when I use NumPy dot, it just give me like element by element, like dot product. Okay. So when I try it, it just works. So I use this. If you don't want to use this, you can do sum equal to 0 and do the for loop. It's the same thing. Okay. So this term is to get this summation. Okay, and we do the summation from k equal to 1 to k equal to j minus 1. Where do we say that in the code? We do k equal to 1 to k equal to j minus 1. Is it here Yes, it is there. Why should it be there? Okay, range I. What is range I? So this means 0, 1, 2, 3, 4, 5 until I minus 1, right? Okay. So when I do from to I minus 1, this means I didn't cover for every I. I is from 1 to n. So when I do this, it is this R. Okay. And I specify the index from here, from this range itself. So when I equal to 1, it's a range of 1 to 1. When I equal to 2, it's a range of 1 to 2. See, 0 to j, all this. How do you understand my code? When you just read it, it is difficult to understand. So to really understand it, what you will do is, you copy just one part of the code. Okay, press Shift Enter in Python notebook, and it will show you what's the result. So that way, you can actually understand how it works. Okay, but basically when we do this, into this, let's just do the trick. Just not many lines.
So if you say shift enter,
Shift tab give me information of the object. Shift Enter is execute that cell.
yeah, but for execute one of these,
You run, if you copy just one part, it won't run. You need to specify what is the j value, what is the I value, and you try to follow it step by step. Only that way that will make you understand. Okay? But there are other ways to write it too. Okay. We will talk more about this when we go over the code and when we are in 212. Alright, for now, let's assume that do this, it works. How about that? Okay, how do we do forward and backward substitution? So first one we have Ly equal to B. We need to do forward substitution, right? So forward substitution, the formula is very similar to backward substitution, but it's just the way that you do the summation. So previously, for backward substitution, what do we do? The general form is we do from I equal to n minus 1, n minus 2 until I equal to 1. Okay, but this time, this is backward, right? So we start from the back when we do backward substitution. This time, the general formula, they're the same, but we just do forward. See? This is the so this is the formula that we have, but we start from I equal to 1. See this index, I equal to 1 to I equal to m minus 1. Previously, when we do backward, we do j equal to I plus 1 to j equal to n. And I have to start from the back. But this time, I start from the front. So we do this one first. We do x1 equal to b1 divided by r11. So we solve this equation first. Then we solve this equation later, and so on. So it's just the opposite of the backward substitution. If you understand the backward substitution already, this is just fine. Okay. And the way that we put in the code, we'll see the code later. Question. No question until you see the code, right? That's the part that you have question, but you understand the idea. So the idea is, hey, how do we do LU decomposition? We have to start with the formula. To get the formula, we multiply two matrices together, and we get the formula by solving it one by one. And then we do forward and then backward substitution. Okay. Then we can solve and get the answer for system of linear equation. How do we get determinant? Do you want to get determinant sometime? Yes? Do you want to get determinant? So if determinant equal to 0, what is it telling you? It tells you something? Do we have inverse for the case where determinant equal to 0? Yes or no? No inverse. Okay. If the inverse equal to 0, determinant equal to 0, then you don't have inverse. Okay? So sometimes you want to get the determinant. To get determinant, how do we get determinant numerically? So first step, let's review how do we get it analytically. Determinant can be calculated from the summation of cofactor multiplied by the pivot element. So we have A as a pivot element, then we delete row 1, column 1, right? And we get determinant of whatever is inside. So which is that one. Then we have plus minus 1 raised to the power of I plus j. You remember that? So and then we take the pivot element, which is B. B is in row 1 and column 2. 1 plus 2 equal to 3, minus 1 raised to the power of 3 equal to minus 1. That's why we put minus 1 over here. So pivot element go here. And then we delete this column and then this row. And then we get determinant of the rest. And we keep doing it until we do all the pivot element in that row. So this time we select row 1. Then here's the formula, analytical form. Derivation of that, I don't know, just memorize that. Okay, this is just a formula. You accept it? Yeah, okay. That's the formula. Determinant of either L or U is the product of its diagonal term. Good? Determinant of either L or U is a product of the diagonal term. What does it mean? So if I have that multiplied by that multiplied by that, that's the determinant. Okay, or you have that multiplied by that multiplied by that, that's the determinant. Okay. So let's take a look at L. So how do we get determinant? I select that as a pivot element. So I delete column 1, row 1, and I get determinant of the rest. So determinant of 1, 0, and some constant 1. What is that? You have downward multiplication, that multiplied by that minus that multiplied by that, right? L32 multiplied by 0 equal to 0. So this means the first element is 1 multiplied by determinant of that, which is 1. Right? Minus B, which is 0, multiplied by determinant of the rest. I don't know what that is, but 0 multiplied by something else is 0. Plus C, which is 0, multiplied by determinant of the rest, is 0, right? So we get 1 eventually. Determinant of P is minus 1 to the power of S, where S is the number of times that switching occurs. P is a permutation matrix. Sometimes we need P. When do we need P? Okay, when do we have to switch to row? When do we do pivoting? We do pivoting, partial pivoting. Okay, look at this. If the diagonal element is 0, whenever you have diagonal element equal to 0, what do you get? in your formula, sometimes you have to divide it by U22. You see that? So U22. So if I have, look at this, U11. U11 equal to A11. So divided by 0, we get not a number, NaN. So you don't want that. So whenever anything in the diagonal term go to 0, we have to switch. When we switch, we can call it like multiplied by permutation matrix. So if we do permutation of P is minus 1 to the power of S. What is P, what is S? Let's take a look. Switch 1 and 4, switch row 1 and row 4, then switch row 1 and row 2. So how do we do that? We do P1 multiplied by A, and then P2 do left multiplied by that whole thing. What is P1 and P2? So switching 1 and 4, that is for switching 1 and 4. Why is that? So when we switch 1 and 4, if you take a look at the matrix, it's similar to the identity matrix, right? It's similar, except row 1 and row 4, they switch. Okay? The rest is the same. If you have any matrix multiplied by that, what you get? You get row switching. Okay? So if you have this matrix multiplied by anything, you get row switching. Okay? And how about this one? It's similar to identity matrix, except row 2 and row 1, they switch. So if you multiply this on the left side of any matrix, the result that you get is a switching between rows, right? These two multiplied together equal to that. So if you want to switch twice, just do this. Okay, and then you are done. Alright. So determinant of matrix P. I want to show you that this formula is true. So S is number of switching. So this time we switch it just one time, right? We switch between row 1 and row 2. So what we get is I get minus 1. So I get, by taking that point, which is row 2, column 2, no. I take that one. What do I do? 0, it should be this. And then, this is not the same, but okay, anyway. Switching one time, odd number cause determinant to become minus 1. Switching even time, get determinant equal to 1. So this matrix is switching just one time. So if I do, okay, I think the red line just moved. I should move this red line up a little bit. So if we delete row 1, column 2, so the pivot element is number 1, right? And it multiplied by minus 1 raised to the power of 3. And the determinant will be 1 and those two. Get it? Then we get minus 1. Why do we care about that determinant thing of switching? Because sometimes we switching two rows. Okay? John, let me stop and